How are you guys doing? We are doing the 2011. This is for the A, B, and BC number 2. And so this is a data table problem. So we know H is differentiable. We know the units. We have degrees and minutes. And so part A, we want to approximate the rate at which the temperature of the T is changing at 3/5. So we need to recognize a couple of things. So the rate, we want to find, let me do part A. So approximate the rate, in other words, approximate the derivative of H at 3.5. And we're going to do an approximation. But if you look, 3.5 is between 2 and 5. And we don't have the function H. So the only way we can really approximate is doing the average rate of change. I know I've done this a lot, but I'm going to do it again. If I plot these points, I want you to have a visual of what's going on. So say that's 66, then it drops to 60, then 52, then 44. I know it's not proportional. And then 43. That's going to be 2, 5, 9, 10. So what is the derivative? Well, let me draw some kind of a curve. So the derivative is the slope of a tangent line. So at this point here, we want the slope of a tangent line at that point. So clearly, didn't do what I wanted to do. If I think it dropped faster. Nope. Is it this one? No. I'll just pick a shape. So if we find the slope between these 2 points, that will approximate the slope of the tangent line. So basically it's the average rate of change. So we're going to find the average rate of change between 2 and 5. That's h of 5 minus h of 2 over 5 minus 2. And again, I require this step because you need to show me where the numbers are coming from, not appearing magically. H of 5, you can replace that with 52. H of 2 is 60. That comes out to be negative 8 over 3. So that'll be your rate. Let's read the question to make sure we answered it completely. Approximate the rate at which the temperature T is changing. Show the computations. It does not ask for units, so you don't have to put units. So we're good at that stage. If you want to put units, that is perfectly fine, but we don't have to. All right, let's keep going. Part B. Okay, you need to recognize this. That's average value, the integral divided by the width from 0 to 10. So that's going to be the average value of H. They want trapezoidal to estimate this, so we'll do that first. So 1/10 of the integral from 0 to 10 of h of t dt. Now, do not forget the 1/10. Very common for people to forget the 1/10. All right, trapezoidal. So I am going 0 to 10. I'm going to pick these two. Ooh, interesting. Can I move that? So I want to find the area. Now, this might be kind of cool. It didn't do what I wanted to do. Let's try that again. Oh, almost. Whoa. So let's try that again. There we go. So the formula, that is a trapezoid. These are the parallel sides. I'll call that H. Whoa, that's not cool. H1. Let me get rid of this mode. H2. I'll call that delta X. The area of that is like kind of like a triangle on steroids. It's 1/2 base time, the H's instead of the base times height. It's going to be 1/2 the heights, sum of the heights, times the width. So we're going to apply that a few times here. 4 times? That's kind of ugly, but oh well. So hopefully I don't run out of room. H1 and H2, it's going to be, these are basically the value of the function at those 2 points. So H1 will be H of 0 and then H of 2. So that's the height, sum of the heights. Delta X is 2, and it's 1/2 on all of these. So the next two, I'll alternate colors, will be between 2 and 5. So that's going to be H of 2, H of 5, and the width is 3. And then the next two will be 5 and 9. Oh, I meant to go back to my old color. H of 5, H of 9, it's 1/2. And the width between those two is 4. One more. The last two are going to be 9 and 10. So, H of 9, H of 10, and the width between those two is 1. So now I have to plug in the actual values. So it's going to be 66 and 60 over 2, and the width is 2. And the next two are going to be 60 and 52, and the width is 3. The next will be 52 and 44, and the width of that's 4. And the last one's 44 and 43. And the width of that is just 1. At this point, I'm done. That is the answer. I don't have to simplify it. But if you do, it's 52.95. And that will be the approximation. So I need a squiggly because it's an approximation, not an exact. Now, let's go ahead and reread the question. We still haven't done this part. Explain the meaning. So let's get the units while we're at it. So this unit right there, that's the width, that's the time. That's going to be the units of minutes. That's that. H of t is going to be degrees Celsius. And dt is going to be minutes again. So those will cancel. So it's just degrees Celsius. Uh-oh, that should be over here. Degrees Celsius. So recognizing that this is the formula for average value. So it's the average value of H. But what is H? H is the temperature of the tea in the pot. So since this average value, H, is the temperature of the tea, so the average temperature of the tea in the pot is 52.95 degrees Celsius for T between 0 and 10. That's it. As simple as that. So that formula is average value. The function's H. H is the temperature of the tea in the pot. We are finito with part B. Let's go to part C and D. All right. Part C. So this, if you want to find the actual value of an integral, there's two ways that we really do these. Is net area. We can't do that. So the only other way is fundamental theorem. So this is actually an easy problem. The fundamental theorem says first you find the antiderivative of that, which is just h of t. And then it says you plug in the upper limit and lower limit and subtract. So that's just h of 10 minus h of 0. H of 10 is 43. H of 0 is 66. Now, they want units. So let's evaluate the units here. H prime, that's going to be change in H over change in T. That's going to be degrees Celsius over minutes. And time is minutes. Those will cancel, so it's just going to be degrees Celsius. So 43 minus 66, is that negative 23, I believe? Negative 23 degrees Celsius. What does this mean in the context of the problem? So we've talked about this quite a few times, but the integral of a derivative gives you, let me see if I get my little mouse connected. It's not connecting, so we'll do that later. So when you integrate a derivative, it gives you the change in what it's the derivative of. So the derivative integral of h prime gives you the change in h. What is h? The temperature of the tea in the pot. So this is going to give us change in temperature of the tea in the pot. So the temperature of the tea in the pot, it's negative 23, so decreases by 23 degrees Celsius from t equals 0 to t equal 10. Done. Part D. Oh no, I need to get a calculator for this. I don't know where my calculator is. I'll find it. It's hiding here somewhere. So part D, try to look for my calculator and do this problem at the same time. It's got to be here somewhere. Where are you, calculator? Daiso! I just saw it a second ago. Oh, I think I know where it is. All right. I got it. Sorry about that. Part D. At time t equals 0, biscuits with a temperature of 100. So the temperature of the biscuits is 100 degrees, and they're in the oven. The temperature of the biscuit is modeled. Okay, so let's see. The temperature of the biscuit at time t is modeled by differential function b. So b is the temperature of the biscuit. This is the rate of change of the temperature of the biscuit. So how much cooler are the biscuits than the tea? So what it's actually asking for is the temperature of the biscuits after 10 minutes. So we want B of 10. So B of T in general is the starting temperature plus the change in temperature. The starting temperature, we're told, is 100. The change in temperature, you integrate the rate of change of the temperature, gives you the change in temperature. So we want to integrate from 0 to T and the rate of change. And since T is used already, I have to use X. So to find B of 10, I just replace, that is oopsie. To find B of 10, I would just replace T with 10. And you pop that in your handy dandy pocket calculator, and we get the answer of approximately 8.817. No, liar, liar, pants on fire. I just lied to you. That's the actual difference in temperature. This on the calculator gets you 34.18275. So that's the temperature of the biscuits after 10 minutes. We found the temperature of the tea. So you want to find the difference between those two. Since the biscuits are hotter at 34, and the question asks, how much cooler are the biscuits? We just subtract that. So now we're going to do 34.18275 minus 23. And that's going to be 11. What am I doing? My H of 10 was negative. No. Poopers. Sorry, guys. I'm not even thinking, I'm just doing. So let me actually think here. So we want the temperature of the biscuits, or temperature, of the tea at 10. So let's do this. It's going to be H of 10 is the temperature of the tea minus B of 10. And H of 10 you get from the table, 43. And then B of 10 is 34.18275. If you subtract those, you get 8.817. That's the difference in temperature between the biscuits and the tea. Dunno. Sorry about that. Took longer than I wanted to, but that's it.